This is the second of two videos in an introduction to infinite series. In the first video, we defined what an infinite series was and we discussed what it means for one to converge. And we also looked at geometric series and how to determine if they converge and how to find their values. In this video, we're going to look at telescoping sums and also something that's known as the divergence test, something that will help us determine when certain series will diverge. Our first example, we're supposed to use partial fractions, something that we learned way back in integration techniques. And we're supposed to do that to write a formula for the partial sums of the series, where we look at go from n equals 1 to infinity, 4 over n squared plus 4n plus 3. Once we've done that, we'll show that the series converges and we'll find its value. Now it's a little bit deceiving here, and we're going to write in two different places here. I want to look at s sub n. This is the sum of the first n terms. The problem is, it's kind of weird because I've got the subscript n, I've got the index n that deals with sort of the variable for the general formula for any given term. So over here on the side, I'm really going to think about this as the sum. We can just use a different variable, right? K equals 1 to infinity of 4 over, what do we have? K squared plus 4k plus 3. I'm going to think about it that way instead with a different variable so that I can look at s sub n where I add up the first n terms. Okay, so s sub n, here's why I made that little change, is going to be the sum. K goes from 1 to n, 4 over k squared plus 4k plus 3. We're going to see some interesting things happen with this. So here we're really working on part A of this problem. We're going to use partial fractions to decompose this rational function into two other rational functions with linear denominators. So what we do first is we take the denominator and factor it. It will become k plus 3 times k plus 1. And, well, then that becomes a over k plus 3 plus b over k plus 1. The method of partial fractions says if you have a rational function like we do, and the denominators are k plus 3 and k plus 1, you can make them two different fractions. The numerators will always be of degree at most 1 less than the degree of where we are now. So here I'm at degree 1. The numerator will be at most a constant. Okay. One method for solving this was to multiply both sides by the denominator of the left side, which eliminates that on the left side, leaving us with just a 4. On the right side, when I multiply a over k plus 3 by k plus 3 times k plus 1, the k plus 3's will reduce, and we just end up with a times k plus 1. And a similar thing will happen with the other one, where we'll end up with b times k plus 3. One method to do this, or one way, is to say, hey, let's let k be equal to certain values that will eliminate variables. For instance, if k is equal to -1, then I'll get 4 equals b times 2, because when I put -1 here, I would get 0. -1 plus 3 gives me that 2, which tells me that the value of b is 2. On the other hand, if k is -3, I'll get 4 equals a times, well, -3 plus 1 is -2, and -3 plus 3 will give me 0, so that term will go away. Again, -3 plus 1 gives me this -2. When we divide both sides by -2, we end up with a equals -2. Okay, so what I'm going to do is I'm going to rewrite this sum here. So it looks like the sum k equals 1 to n of, I'm going to do it so that the positive constant is first, right? That's the term with the b. So we're going to put the ones with the b in there first. So we'll have b over k plus 1 is 2 over k plus 1, plus a over k plus 3. Well, that's minus a is 2, well, a is negative 2, so that's why we have minus 2 over k plus 3. Okay, so I'm going to do this. I'm going to explain at the end why I've made some choices that I make. I'm going to write two terms at a time. Now, why am I doing that? I'm going to tell you what I'm looking at that makes me understand that I'm going to do that. At the end, I'll explain why I made that choice. So if I look at k plus 1 and k plus 3, they're 2 apart. That's why I'm making this choice of doing 2 at a time. You'll see why it works out nicely. So we'll end up with, when k is equal to 1, we get 2 over 1 plus 1 minus 2 over 1 plus 3. When k is equal to 2, we'll have 2 over 2 plus 1 minus 2 over 2 plus 3. When k is 3, now I'm going to write this on a new line. Again, I'll explain why in a moment. When k is equal to 3, we end up with 2 over 3 plus 1 minus 2 over 3 plus 3. When k is equal to 4, we get 2 over 4 plus 1 minus 2 over 4 plus 3. I'm going to do one more line of this. It's kind of snoozy. 2 over 5 plus 1 minus 2 over 5 plus 3 plus 2 over 6 plus 1 minus 2 over 6 plus 3. Okay, so then we're going to take a little break. Okay, I'm going to write two more lines here. And then we're going to do some simplifying. The very last line, I'm going to let k be equal to n at the very end. So the last one, I'll have 2 over n plus 1 minus 2 over n plus 3. In the term before that, k is equal to n minus 1. So we would have 2 over, this is weird, n minus 1 plus 1 minus 2 over n minus 1 plus 3. The term before that, which will go on the line above it, is 2 over n minus 2 plus 1 minus 2 over n minus 2 plus 3. And then before that, we would have 2 over n minus 3 plus 1 minus 2 over n minus 3 plus 3. Woo! Okay, so pause for a moment. Don't really pause here, but now let's evaluate all of this. Okay, this could have saved us time had we done it before. Let's look at the first. We end up with 2 over 2 minus 2 over 4 plus 2 over 3 minus 2 over 5 plus 2 over 4 minus 2 over 6 plus 2 over 5 minus 2 over 7 plus 2 over 6 minus 2 over 8 plus 2 over 7 minus 2 over 9 plus, and then we have a bunch of terms we'll just take a break on, and now we've got to be careful here, plus this is 2 over n minus 2 minus 2 over n plus 2 over n minus 1 minus 2 over n plus 1 plus 2 over n minus 2 over n plus 2 plus 2 over n plus 1 minus 2 over n plus 3. Okay, so this is why I chose 2 at a time, because it lines things up so that we can see them knocking each other out. Here I have minus 2/4 plus 2/4, and minus 2/6 and plus 2/6. I have minus 2/5 and plus 2/5, minus 2/7 and plus 2/7. So I like to draw it in red. Those will cancel. Those will knock each other out. Negative 2/5 and positive 2/5 cancel. Negative 2/7 and positive 2/7 knock each other out. If I look down towards the bottom, we end up with the 2 over n minus 2 over n there. So those knock each other out. We end up with 2 over n plus 1 minus 2 over n plus 1 there. Those knock each other out. And then we have this dot, dot, dot business. There's a bunch of stuff going on there. I mean, if n is really, really large, then of course we'll have a minus 2/8, and there will be a plus 2/8 and all that business. And there would also be a plus 2/9 down there. And then down here towards the end, we would have the 2 over n minus 2 and the 2 over n minus 1. Those would have matching minuses or opposites in the dot, dot, dots. Those will cancel like so. And so the only things that survive when we have a final answer, and it's really nice because the answer to part B is very short, but we have S sub n is equal to 2 over 2, which I'm just going to call 1, plus 2/3. And then the only other ones that survive are these two terms. And so it becomes minus 2 over n plus 2 minus 2 over n plus 3. That's what the nth partial sum is. So if I really want to, and I don't have any desire to, I could figure out what the 100th partial sum is. It would be 1 plus 2/3 minus 2 over 102 minus 2 over 103. Okay? All right. So that's kind of a nice, very rigorous way of doing this. Now for part B, then we are asked, hey, let's find out what that sum is. Well, we want to look at the limit as n goes to infinity of S sub n. So this is the limit as n goes to infinity of 1 plus 2/3, which I guess I could have written as 5/3, minus 2 over n plus 2 minus 2 over n plus 3. Well, as n goes to infinity, that goes to 0, this goes to 0, and we end up with 1 plus 2/3, which is 5/3. Okay, so this is an example of something that's known as a telescoping sum. It's telescoping because you want to think of those old-fashioned telescopes where you've got this one little circular or cylindrical thing, and then there's another little cylindrical thing behind that, and then another smaller one behind that, and so on. And then when it's time to fold up your telescope, it's just one big cylindrical piece. You know, you push it in this way and push it in that way, and you end up with just one piece to that telescope. So that's like these things canceling each other out. So one thing that's really nice about these examples is that this is one other type of series where we can find the value of that particular series. Our next example is the harmonic series, which is so important that I'm first going to highlight it in red so you can see that it must be important for some reason. And then I'm going to highlight it in green because it really is just that important. We need to know the harmonic series. It pops up over and over again. The harmonic series is just the sum of the reciprocals of the positive integers. 1 plus a half plus a third plus a fourth and so on. Okay? So it's a very simple series. It turns out that the harmonic series diverges. Okay? The harmonic series diverges. And I'm going to show you why, so bear with me here. I'm going to write out the first 16 terms of this. Now that's dedication. There are the first 16 terms, and then of course it continues on. I'm going to group these in a particular way. In particular, I'm going to look for powers of 2 in the denominator, and I'm going to group them sort of according to that. So 1, I'm going to group all by its lonesome. 1/2 also gets grouped by its lonesome. On the other hand, 1/3 and 1/4 will get grouped together. And then I'm going to group all of the next fractions until the next power of 2, so up to 1/8. And this is why I stopped at 1/16, because now I would group to 1/16. I would group to 1 over 32 and so forth. Okay, now I'm going to make a comparison here. Let's replace each of the terms within a group of parentheses with its smallest value in that group. And then we'll make some decisions. So I've done that. Now, of course, these two are not equal to each other. So let's compare them. Think about it. Which of these two sums is going to be larger? If you said the second one, you're correct. The second one is going, or I'm sorry, if you said the first one, that's correct. The first one is larger, and the reason for that is because if I compare 1/2 or 1/3, for example, to 1/4, 1/3 is larger. I'd rather have 1/3 of a pizza than 1/4 of a pizza. The same thing is true all the way down the line. 1/5 is bigger than 1/8, 1/6 is bigger than 1/8, and so on. So assuming that this first guy actually adds up to something, whatever it adds up to, it's going to be bigger than what the second guy adds up to. That would make sense. Okay, so let's keep going. This second line here is going to be equal to 1 plus 1/2. Now let's start doing some work. Here I have 1/4 plus 1/4. Well, that would be 2/4. Oh, that's 1/2. And then 1/8 plus 1/8 plus 1/8 plus 1/8 is 4/8, which is 1/2. Interesting. And then these guys will all add up to 8/16, which is another 1/2. Now think about this. If you're tasked to start off with 1 and then add 1/2, and then add 1/2 again and again and again and again, will you ever stop? Of course not. You'll end up passing any positive number you want. This actually will go off to infinity. Okay, it equals infinity. We know what that means. It doesn't really mean it equals infinity, but it tends to infinity. Well, if the original sum is bigger than the one that we created, and the one that we created goes off to infinity, well, then the other one we create has to also go off to infinity. So it is, as we said, it's divergent. Okay? So if you watched the first video, there was some stupid joke. I've got another stupid joke here about mathematicians in a bar. In another bar across town, the one mathematician comes in and says, "Hey, give me a beer." And the second one says, "Give me half a beer." The third one says, "Give me 1/3 of a beer." The fourth one says, "Give me 1/4 of a beer." And then they keep going. And finally the bartender says, "Hey, cut it out. Get out of here, guys. What are you trying to do? Ruin me?" Okay, it's a joke. Somebody calls it a joke. And what they're really saying is the bartender cannot fulfill all these requests because if you add these up, of course, we're infinite. Okay, so what I really, really, really want to emphasize is here we have a really peculiar series that I'm telling you now will pop up over and over again that diverges. This peculiar series is the sum of the reciprocals of the integers, the positive integers. Okay, and this is why it's so peculiar. The next theorem says that if a series converges, if this series converges, then the terms must go to 0. Okay, if the series converges, then the terms must go to 0. Now, we just saw the series 4 over n squared plus 4n plus 3, and I think we said that was equal to 5/3. It converged, right? It converged. Which means, according to this theorem, that the terms 4 over n squared plus 4 plus 3, 4n plus 3 that is, those terms must go to 0, and they do. Okay? Now, here's the danger. Just because the terms go to 0 doesn't mean the series converges. The harmonic series is a classic example of that. 1 over n. If n is really large, that's almost nothing. The terms go to 0, but the series it still diverges. Okay? So you've got to be super careful. All right, little mathematical language break. If we say if P then Q, and you hear this all the time, if I lose 50 pounds, then I'm going to take a trip to Hawaii, okay? The statement, if not Q, then not P, is called the contrapositive of the original. So I said, if I lose 50 pounds, then I'll go to Hawaii. Well, I'm going to move the Hawaii business to the front and say that doesn't happen. If I don't go to Hawaii, then I didn't lose 50 pounds. That's kind of sad. But you can get a sense that those two feel like they're saying the same thing. If I lose 50 pounds, then I'll go to Hawaii. If I don't go to Hawaii, then I must not have lost those 50 pounds. These are what we call logically equivalent. Either they're both true or they're both false statements. The statement if n squared is even, then n is even. And the statement if n is odd, then n squared is odd are either both true or both false because they're contrapositives of each other. We move the back end statement, n is even, to the front and negate it. N is not even or odd, or n is odd. We move the statement at the front, n squared is even, to the back and negate it. N squared is not even. In other words, n squared is odd. So just for a little practice, state the contrapositive of the statement if x is greater than or equal to 10, then x squared is greater than or equal to 10. Well, we're supposed to take the statement at the back end, I'm going to highlight that in green, and move it to the front end and negate it. So if x squared is not greater than or equal to 100, then x is not greater than or equal to 10. What did we do there? We took the first phrase and negated it at the back end here. Okay. Now, we might be able to tidy that up. If you're mathematically inclined, you might say, well, that's the same as saying if x squared is less than 100, then x is less than 10. Okay. Now, think about the original statement. Is it true? Is this statement a true statement? If x is greater than or equal to 10, then x squared is greater than or equal to 100? Yeah, that's true. And so this must mean the same thing here. This must also be true. If x squared is less than 100, then x is less than 10. That's true. Now, you might be a little suspicious of those negative numbers. Hey. Negative 9 squared is less than 100. And negative 9 is less than 10, so be careful there. If we go back to the statement of the theorem we just talked about, let me write it again. The theorem stated that if the series converges, the series of with terms a sub n, if that converges, then the terms go to 0. Now, if we look at the contrapositive of this, we would say, hey, if the limit of a sub n does not equal 0, well, when we look at the negation of that would mean that if the limit of a sub n either does not exist or does not equal 0, that's the negation, then the series doesn't converge. Then the series diverges. This is hugely important, okay? So if the terms do not go to 0, if the terms of the series do not go to 0, then the series diverges. Here's what I often do. I start off with the divergence test. Always make sure a sub n goes to 0 before trying any other tests. Now you're saying any other test. What other tests do we have? We don't have any other tests at this point, other than maybe the geometric series test. Is it a geometric series and that sort of thing? But we're going to learn some more as we go. Always make sure there are some theorems that are going to be helpful. Sorry for the smaller type, but I wanted it to fit it on here. Suppose we have two convergent series, one with terms a sub n and the other with terms b sub n, and then c is just some constant. We can create new series that also converge. So c sub n converges, or c times a sub n will converge. The series with terms a sub n plus b sub n will converge, and the term with a sub n, the series with a sub n minus b sub n will also converge. Okay? And their values are, well, with the c in there, you can kind of pull the c out front. When you have the sum of two terms of the series, you can make that two different series. And when you have the difference, the same thing will be true. This is not true. This is not true if we multiply an and bn. Okay? Probably don't have a lot of exposure yet. You may not be able to come up with a nice example, but it's actually not the case that you can multiply them like that. Okay, so here is our bag of tools so far. We used partial fractions, and we could actually find the value of the sum of a telescoping series. Now, I've made a comment before. Finding the value of the series, what does it converge to, is a very rare question, or it's a question that can rarely be answered. If we have a geometric series, it's going to converge when the absolute value of r is less than 1. R is the common ratio, and we can find the value. Again, a rare circumstance. We can use the divergence test to show a series diverges if the terms don't approach 0. Again, that's always the first thing I check. And then when two series are convergent, the sum and differences of them will converge, as well as the series consisting of constant multiples of those terms. In this example, we're going to put our work into practice. I've got 3 examples that I'll work through, and we want to determine if each of these converges or diverges. For our first example, we've got the sum of 1 plus 3n over 4 plus 5n. So the terms here are 1 plus 3n over 4 plus 5n. That is the term. Okay. What do I mean by that? So that's what a typical sum or a typical sum end looks like when we write out the infinite sum. In order for this to converge, now this isn't evidence, but if it's going to converge, it has to go to 0. That doesn't work the other way. So if it goes to 0, it doesn't necessarily converge. But let's look first of all to see if the terms go to 0. So we've got the limit as n goes to infinity, 1 plus 3n over 4 plus 5n. In the video on sequences, I gave sort of a shortcut, easier way to do this. This is what we would call an infinity over infinity indeterminate form. The numerator is approaching infinity as n goes to infinity, as is the denominator. And what I suggested that you can do in those circumstances is take the term that has the highest power of n in it, assuming that we're dealing with a rational function, a polynomial divided by a polynomial. Take the term that has the largest power of n in it and only keep that term. So we'll have 3n, and we'll keep the 5n in the denominator there. Now, if we simplify this just becomes 3/5, and so my answer is 3/5. And now I've forgotten why I was doing this. I wanted to see if the terms go to 0. If they don't go to 0, it cannot converge. And so this is not equal to 0, so the series diverges by what we call the divergence test. Now, the divergence test can only tell you if a series diverges. It will never tell you if a series converges. So never write the words, the series converges by the divergence test. That doesn't make sense. Okay. For part B, let's look at this. We've got 1 over 3 to the nth. This is my term, minus negative 1/4 to the nth. That's my term. That's part of my term as well. So a sub n is that. We want to look, does this go to 0 as n goes to infinity? So we'll look at the limit as n goes to infinity of this particular creature. Now think about what happens for large values of n. If n is large, 3 to the n is very, very large. 1 divided by a very large number is almost nothing. The same is true for negative 1/4 to the nth, except the sign bounces back and forth. So the first term goes to 0, the second term goes to 0, so the limit is 0. Okay, that is not enough to say it converges. That is not enough to say it converges. Your terms can go to 0, and the series will still diverge. The harmonic series is an example of that. Okay. So now I need to think about this. Well, let's ignore part of this. Let's imagine that the minus 1/4 to the nth isn't there. I have 1 over 3 to the nth. 1 over 3 to the nth is the same as 1/3 to the nth. When you have something that looks exponential, something to the nth power, that's geometric. The common ratio would be 1/3. That would converge. Okay, now let's ignore the 1 over 3 to the nth. This is negative 1/4 to the nth power. Oh, again, it's a geometric thing where the common ratio in absolute value is less than 1, so it too will converge. So what we're going to need to do is split this up into 2 separate sums. We've got the sum n equals 1 to infinity. I'm going to write the 1 over 3 to the nth as 1/3 to the nth, minus the sum as n goes from 1 to infinity, of negative 1/4 to the nth. Both are geometric. And I remember the formula for the geometric series. It goes a over 1 minus r. A is the first term. R is the common ratio. Okay? So in the first one, the first term is what we get when we let n be equal to 1. Okay, so that's the first term. We'll have 1/3 to the first power in the numerator, just to be very blatant about it. In the denominator, our common ratio is the thing that we're raising to the nth power, so 1 minus 1/3. Minus, from that, in the second one, we have negative 1/4 to the nth, n starts at 1, so we'll have negative 1/4 to the first, divided by 1 minus negative 1/4. And when we simplify this, we end up with 7/10. Okay. Our final example, we look at the sum of the natural log of 2 to the nth power. Okay. Now, I pause for a moment. I say, well, let's see, natural log of 2. Natural log of 2, let me think about what it's equal to, or approximately equal to. I remember it's about 0.69. That's sort of related to doubling. You might have heard of the rule of 70 or the rule of 72. It's all about the natural log of 2. If you haven't, look it up. Okay, so the first term would be natural log of 2 to the 0th, which would be 1. The second term would be the natural log of 2 to the first, and then the natural log of 2 squared, the natural log of 2 cubed, and so on. Hey, look what we have here again. We have the same quantity raised to different powers. And so this is, once again, geometric. The common ratio is the natural log of 2, which in absolute value is less than 1. So it converges. Awesome. Once again, we have a convergent sequence. It's geometric. And so we're going to do the first term. The first term is 1 over 1 minus the common ratio, which is the natural log of 2. There's really not a whole lot we can do to simplify that.